Oh, when you're like working with it?
How is the alkene able to learn all of its electrophilic reactions?
Olefin never forget.
Well, it's because an olefin never forgets. Olefin is an old term for alkene. Olefin was mentioned on the first side of that handout. So that was the riddle. There's one reaction on that page that we did not cover. What color was that? What color this is? Iron coral color. HBr and peroxides. Yes. What is that? Some of you figured that out. Some of you asked me about it. If you include peroxides, it becomes a radical reaction and it reverses the regiochemistry. Okay? I did not cover that. We'll cover that here at the very end of the course when we do more radical reactions. Yes?
I had a little bit of trouble like visualizing like the ring formations and like the ring shift. Yeah, it's like in 5 circuits, or like how I could
Like on the quiz?
yeah, like that
Mechanism?
Because like once I make the carbocation, like it's just like hard to visualize how it's like the ring shift.
Ring formation?
Or like the change in like ring structure. The ring fit.
Well, can we make a three-membered ring? Okay. It's a three-membered ring. Each of us is an atom. You are bonded together. Okay. We got you are bonded, we are bonded, and we're bonded. A three-membered ring would have 3 bonds if you drew it. Okay. And you two are bonded. Okay, shoulder or something. But you're not part of the ring. The ring is over here. Okay? But if I broke free here and went over and bonded to her, y'all are still bonded. Now our ring is 4-membered ring. So the bond breaks free and moves over and the ring becomes bigger. Or it could go the other way. We could have a 4-membered ring and I could break free from you and I could say see you later and I could go over here. Now this becomes a 3-membered ring, so it went from 4 to 3. The bond moves. Okay? You'll have to show me specifically what you're having trouble with. Also, when we do the key, didn't the one on the quiz have a ring?
Yeah.
What was it? It was a 3 went to 4. 3 went to 4. Just like this. 3. And we got a. Why would this move out? Apparently, there's a carbocation out there, and the electrons go out to the carbocation.
Oh, when it
No, some mechanism questions you would never be able to predict the product. But given the product shown mechanism. That's very reason. And the product shown may not be the major product. It may be a product of 5%. Guys, but whatever the product is, it's still formed, and you can still propose a mechanism for how it can be formed, even though it's not the major product. There's a difference between mechanism questions and predicted product. You can see some crazy product mechanisms, but still you should be able to rationalize how it can be formed. So it's kind of like a puzzle getting to the end there. The product may look strange, but the steps are not going to be strange. The steps are going to be steps that I would expect you to know if you've done a good job learning material. Standard steps. Sometimes standard steps can lead to, if you put a sequence of standard steps together, you get a very unique product you never would have expected. Yeah.
Good morning. I understand you said you're going to post the key, but would you be willing to work that one on the quiz so we could ask questions in real time instead of after the fact when it might be too late?
Well, I could. I'm interested on the video quiz though. Do you agree that a video quiz is better than me just putting a written key up?
Oh, for sure.
Okay, good. Okay. But since we have a little time, you want to work one in class.
Yes.
I thought you already moved on to test 3 material. Y'all seem to be ready to move on to test 3 material.
No, I declined them all.
So you're looking to revise your
Yes, sir.
the mechanism? The mechanism on the quiz?
Yes, sir. The ring expansion. Oh, and the
Yeah, it's the, okay, we did some examples. Okay, you got an alkene, you got an alcohol. The only chemistry you know is alkene. You got H plus here. Alkene reacting with H plus. Is there any other starting point? Well, in another 6 weeks, we'll have other starting points because we'll learn reactions of alcohols with H plus. We don't really know that now. H plus, alkene. Where are you going to make cation out? Right or left?
left.
Correct. So the electrons pull away from this carbon. Okay. And this gives what? Remembered ring, alcohol, 2 carbons, but we made a bond to H, and we've left carbocation here. We've been doing that for, what, 3 weeks at least? What else would you do to begin with? Anything else?
I guess.
Anybody else do a different first step here?
No.
What did you do?
Oh.
I'm not quite sure what you're going to do there.
You don't have to talk too much. You just
The only reactivity you know is an alkene reacting with H plus. What chemistry did we cover? Alkenes and alkynes. I don't see an alkyne, I see an alkene. What do we, you got alkene and H plus. I don't see how that can be any different starting point. The only question is where are you going to make cation at? Make cation here, right? Secondary? If we make cation there, it'd be primary. Don't do that. Okay. What can happen next? This is aqueous. You got water here, right? Well, water could attack here. Electrons make bond here, but that's not going to give that product. Well, clearly you just have to see that that's a 3-membered ring and it has gone there. Have you ever seen a ring expand? We did some examples. Okay, how could that do that? Well, these 3 students are bonded together. One's sitting next door, though. How about these electrons break free of this carbon and move over there? Somebody pull them over there. How about if I do it with an arrow? Grab them and sort of yank them away and move them over there. Okay? It's like right there. Grab my finger and pull it over there. I'm going to draw the same thing, the same sort of bond angles here. Boom, boom. OH. That went boom, boom. I'll keep drawing in the new H if you want. Instead of this being drawn, it's not quite as, instead of this being here, it's no longer there. Where is it now? It broke free and it moved over. It's like a pin. Moved over there. It needs to be longer because I got some, moved over there and bonded. What's here though now? There's no H there, so there's only 3 bonds and it's a plus there. Electrons moved over. That's what it gives. I don't like to keep drawing that in, at least I don't. Yes, there's now 3 H's there. There's 2 here. There's 3 on the end there. There you go. You can clean this up, make it a sort of better, just a like this. It's a 4-membered ring with an OH here and a methyl here. That's the same thing. Cation here. We got to get to this. What do we need to do? Double bond between oxygen. Can we do a double bond here? What does this look like? What do we call that? That's resonance. We're going to learn about resonance in the handout I just gave you. But guess what? We've talked about it several times up to now. Yeah? And we did that in tautomerization. We did that in a few different things. We got to get a double bond here. Even if I didn't know where I was going, I would know there's resonance here. Because physics, electrons are going to be attracted to a positive, and we can actually show a bond forming here. And now we got double bond here. H's don't magically disappear. The other lone here didn't magically disappear. There you go. Charges though, the oxygen is positive. Are we getting closer to home?
Yes.
What do we need to do?
Water.
We need to take this H. What you take it? Same old answer. It can be either be the HSO4 minus that can take it, or you can use water to take it. Because how does sulfuric acid exist in water? H3O plus. So you can form H3O plus. These electrons take the H, these electrons stay behind. Classical acid-base reaction, what does that give? That gives that. What do we form? H3O plus. What minus sits with that plus? HSO4 minus, which sat with that. I didn't show it over there. Again, that's how sulfuric acid actually exists. Or you could use that and reform H2SO4. That's about the 28th time I've mentioned that. What do you do? You seem to have had trouble on the course. Where did you have trouble?
Well, I mean, when I'm rushing, you know, that doesn't help me. But also I think when you make that 4-member ring, or 4-sided ring, whatever, you can tell it's 4 sides, but then you're looking at a square, right? I know that sounds silly, right, in the moment, but you see what I'm saying? Like, it doesn't look like a square at all. It looks like a, I don't know what that looks like.
What?
Good way to do it is
You mean this square box here?
No, what I'm saying is when you do the alkyl or whatever you call it shift, right? And then you have that ring, and I guess in the moment, I'm like, this is not a square.
Look, what size ring is that?
You're right. No, I get what you're saying.
It's a 4-membered ring.
Right. I just need more practice, clearly.
But the 4-membered ring, though, I mean, this bond is like twice as long as that one. That's because it's not as strong as the board.
Right.
I drew it like that, so I wanted to keep everything the same. I just wanted to move these over and say, instead of these electrons connected between these 2 carbons, if the 2 electrons break free of that carbon and bond there. And I tried to draw the same thing over there.
Sure.
Ring expansion. How we do on that? Okay.
Stop lying, y'all.
Classical mechanism with some resonance in it, and okay.
So I have a question on the second part of each resonance, where we go from like the resonance.
And I get -1 here because what did I do wrong? Because this is resonance, I need a resonance arrow. Appropriate use of arrows. When you go between resonance structures, a double-headed resonance arrow.
So at the resonance structure, before resonance, I was wondering why we didn't do O, open up the bond between O and H, with an H2O and take out the H, and then do an O minus. And
You want to remove this H from water?
Yeah, first, and then.
It's not acidic. And you want to make an anion?
Yeah.
Okay.
Because the anion.
Yeah, never make anions under acidic conditions. Strong anions. You can have sulfate anion because sulfate anion exists. That's how sulfuric acid exists. You can have Cl minus because that's how HCl exists. But at some point, if I haven't told you already, I'll give you some more tidbits. This is probably an organic too. Under acidic conditions, all your ions are going to be positive. Positive, 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 positive. Under basic conditions, ions will be negative. Or neutral. Again, the only minus you can have under acidic conditions is minuses that exist under acidic conditions. And those are the conjugate bases of acids. Those are the only ones that can exist under acidic conditions. Basically, if you want to make an O minus here, it's going to look like this, an O minus. You're telling me that you can have this under acidic conditions? What is this? It's hydroxide. You're telling me you can have hydroxide under acidic conditions? Now, somebody may have told you that, but they just wanted to do some math. It's like reaching into hot water and saying you're going to get some cold in it. I mean, you can argue theoretically there's cold water in a pot of hot water, but in real life there ain't. So there's a disconnect. There ain't no base in acid. All right? So you would never form this or this under acidic conditions.
Can we do number 3 after we're done?
I'm going to have to do a video key. Okay? So you need to move ahead. This was mainly to give you a chance to see how you're doing. Did you take this and I don't know any of this, or did you take this and feel confident that you're ready for Wednesday? Or was it somewhere in between? Wherever it is, keep working and get ready for Wednesday. Okay? Okay. Everybody get a handout today? Okay, I sent you 2 by email. One was mass spec. Mass spec.
Oh.
Okay. There's a mass spectrum of an alcohol. I think it's just one video, kind of a long one. It's dividing it into 2, whatnot. But mass spec is very important, and again, I'm doing more topics by video, and I think it's good. I've mentioned this before because you can watch it at your own pace, you can watch it multiple times, etc. It's there. I think mass spec is particularly good for video because there's lots of fine details, and when we're rushing in class, these details get missed. Okay? You can take more time, rewatch. The other is because I'm going to be out on Monday is I thought I might do resonance, but we need to start resonance today. Instead, I'm going to do some dying chemistry. Test 3, we begin with resonance handout, and then we move to this one. This one I'm going to start by the video. Okay? That's not posted yet. But that'll basically be in lieu of class on Monday. Okay? Chemistry of dienes. Dienes, well, they're going to be twice the fun, but not an alkyne. That's an alkene. Well, there's another alkene. Because there's 2, it can be called a diene. What if you had 3 alkenes? Triene. Tetraene. If you had a lot, you might call it a polyene. Okay? Also conjugated. These are conjugated. We need to look at that. Resonance. Okay? I sent you both of these by email, and I want you to print those on your phone. I'm not going to distribute those to you in class. Okay? When I say print them, some of you maybe like to have them on electronic device. That's okay. I don't know what printing means to you, but basically when I say print, that means have them available as you would like them in class. Okay? So if I show it, you want to have it there. It doesn't necessarily have to be printed. Okay, resonance. Have we talked about resonance before? I mentioned we would cover it for test 3. Well, guess what? The time is here. All right, this is test 3 material, new material. But there was a little resonance in test 2. Enough to do some stuff. There was resonance on the quiz. We did it. Double-headed resonance arrow, yeah? Okay, we'll look at resonance. As I mentioned, a lot of books cover resonance in chapter 1, 2, or 3, and it's included on test 1. I don't do that because I think you need to get a little more experience with structures and stuff. Okay, we build up to it. So you see in the book, the Klein book, it's covered in chapter 2 some real early. Then it comes back and it hits more way over here. 17. I kind of do everything together, sort of. I'm placing it like about chapter 8, 9, and 10. Okay. I will point you to the very back. If you like free information from me, here's some here. I call it the Golden Rules of Resonance. Okay? A summary of some important things to remember, to don't do, etc., etc. All right? No extra charge for that. All right? As we mention things, I'll say it's probably on the Golden Rules of Resonance page. Okay? What's number 1 on that page? Only move pi electrons. When you're doing resonance, we're dealing with pi electrons, not sigma electrons. If you move sigma electrons, you're not doing resonance. Okay? What's number 2? Don't move any atoms. If you move an atom, you ain't doing resonance. You only move pi electrons. Number 3. All resonance structures have the same net charge. Okay? There's 1 through 6 there. They're all important. Okay, let's get going here. Also called what? Delocalized bonding or pi bonding. Start with neutral alkene, conjugated alkenes. Stability of conjugated dienes. Conjugated, okay. Both of these are dienes because they each have 2 alkenes. One of them, though, is conjugated, one of them is not. They're non-conjugated. What is conjugated? Well, isn't this 2 p orbitals, 1 electron each, overlapping? Isn't that what a pi bond is? And you see that there's a pi bond there? Because an alkene consists of what? A sigma bond plus a pi bond. All right? Now we covered that week 1. You had 6 to 8 weeks to understand it. Right? Over here, we also have a pi bond. 1 electron makes pi bond. Yes, 2 pi bonds. But guess what? These 2 p orbitals are sitting next door to each other, just as close as those 2. Are they interacting any? Is there any interaction here between the 2nd and 3rd p orbital? Any interaction? Or are they busy interacting and making bonds inside? The answer is yes. They're interacting. And so, is there a pi bond between carbons 2 and 3? Well, p orbitals are interacting. That's part of the pi bond. Well, why didn't I show it? It looked like it's just a single bond. That's because when you start doing resonance, a single structure is no longer fully accurate. Okay? In the end, what does conjugated mean? Conjugation refers to p orbitals. P orbitals lined up, like toy soldiers. 4 p orbitals conjugated. That's how we can describe this. 4 are all lined up. And all 4 are overlapping. But the original Lewis structure, before I wrote on it, doesn't really show that. Anytime you have resonance and conjugation, a simple Lewis structure becomes deficient. It doesn't show this. You got to just know it's there. Okay, over here, conjugation. We have an alkene here. Yeah, 1 electron, and we have an alkene here. Okay. Are the 2 alkenes conjugated? No, because do you have a p orbital on this carbon? No, it's sp3. There's no p orbital on this carbon. And so because there's no p orbital there, it kind of breaks the connection between the two pi bonds. There's no continuous connection. So we say this is two isolated pi systems. The alkenes are isolated. They're not conjugated. But these are. Which is better? Well, conjugation is better because more orbital overlap. The more orbital overlap you have tends to be better. Until we get to organic 2 and talk about anti-aromatic compounds where orbital overlap is bad. The starting point is it's good. More electron orbital overlap better. How can we determine this? What about a heat of hydrogenation? You can hydrogenate these. Hydrogen. Both of these would become 1, 2, 3, 4, 5. Was it 1, 2, 3, 4? Both of these would become pentane if you doubly hydrogenate them. They become the same thing. But this one gives off more heat. So which is more stable?
First one.
The conjugated one, because it gives off less heat. It had less to give off. You understand what an H and H mean. Okay? So this is a quantitative number. It's redundant. It's a number that answers the question of which is more stable. Conjugated diene is more stable. It sits at a lower energy than the non-conjugated. Conjugation is a good thing. Okay. Benzene ring is fully conjugated. All 3 double bonds conjugated here. If you look at it, you have 6 p orbitals in the ring, all overlapping with each other. And since it's in a ring, it leads to what we know as aromatic. And we'll talk more about that in organic 2. But right now, you know that it is a fully conjugated system. What about this structure here? Is it conjugated? Well, I've already told you the answer. Why is this not conjugated? Why are these 2 alkenes not conjugated? Because if you look at this, what's the hybridization of the central carbon? sp. 2 regions, sp. Linear. How many p orbitals does this carbon have? 2. Okay? All this goes back to week 1 stuff. But I've given you 2 months to learn more week 1 stuff before we start using it. Okay? Can you imagine talking all this like 10 minutes after we first presented all of the other? Okay? So you've been working with this stuff. We got a central carbon. Okay, let's put 1 p orbital there. The next door carbon is sp2. It has a p orbital. 1 electron makes pi bond. I won't draw the 2 H's there. But then this is sigma bond over here. How's the second p orbital here compared to the first one? How's it positioned? It's perpendicular. So if that's flat on the board, the next p orbital is coming out towards you and going back. Half this way, half the other way. Now, it's hard to draw that. So I may not draw it. But it's coming out here, half out, half going the other way. It's making pi bond over here. Well, how is this one oriented? It's actually also oriented this way. And these are overlapping to make pi bond here. Okay, sometimes you just sort of draw it sort of slanted. And if you can imagine it, instead of slanted like that, it's really supposed to be back and forth. Those are overlapping there. Maybe I can do it up here. Yeah, these pins will stand up. Everybody see? Central carbon has 2 p orbitals. And if you can see that, that is how the compound is. Two p orbitals like this making pi bond, and two p orbitals like this making pi bond. And the one in the middle has two. But see, these two systems are perpendicular to each other, and they're not conjugated. Because importantly, to have full overlap, how do p orbitals have to overlap? All like this. Okay? Like that. Those are overlapping. What about here? Are they overlapping here? No. So this is really two different alkenes that are positioned like this, and they're not conjugated with each other. Right? So if you understand perpendicular p orbitals and whatnot, that's called accumulated diene. When you got a very weird-looking carbon that's double bonded on both sides. Okay. It's not a common type of compound, but it is known. Okay, closer look at conjugation. A lot of this is just background. There's two parts of resonance. There's theory, understanding the orbitals that are there. Okay? Number of electrons. Drawing things like that and understanding. That's part of it. The other thing of resonance is doing it on your paper and drawing resonance. All right? Right now we're kind of looking at the theory. Conjugation. Really, I may not need to repeat this. It's the same thing as up there, except just missing here. A methyl. One thing we can ask, though, is questions like this. How many p orbitals in this conjugated system? 4. I drew them up there, didn't I? 4. How many pi electrons in the conjugated system? With 4 pi electrons, right? Who said 8? Somebody said 8, right?
I did.
Who did? Why 8?
But you're supposed to double it because it's 2 electrons.
No, we drew it up above. This is p orbital. 1 electron, 1 electron. How do you make a bond? 1 electron interacts with 1 electron. 2 electron covalent bond. You agree?
Yeah.
Okay. A pi bond consists of 2 electrons. 1 on each atom are interacting to make the covalent pi bond. It's the same as above. We've already showed this. There you go. There's your 4 p orbitals. Each p orbital has 1 electron. Thus, there's 4 pi electrons. Pi electron is an electron that's in a p orbital. Okay? Really, this is all kind of just all on top of each other. I could draw this here. I'm drawing it here. Ultimately, the important statement is, once things become conjugated, it really becomes one system. And this is what really, this looks like 2 individual alkenes. What you have to know is that once all these are conjugated, it becomes one system that consists of 4 p orbitals with 4 pi electrons in it. And the electrons are really smeared all the way across the 4 orbitals. Delocalized bonding, high bonding. And I'll give you an analogy. It's sort of like a garden hose in your yard. Okay? And you put water in that garden hose. And the garden hose is 4 feet long, and maybe you put 4 pints of water in the garden hose and tap it off. How's the water going to spread out in that garden hose? Everybody would probably say it's going to fill the garden hose sort of equally. Well, that's what you got here. The electrons are just in this system, and they're all there. Okay? It becomes one system, like that question.
So they fully share.
Yeah. And once we get to this type of discussion, it becomes molecular orbitals type. We're getting closer to that. All right? And we're pushing towards advancing up to that. If you want to read about molecular orbitals, that's where you have an orbital that's spread over the entire molecule. These are atomic orbitals. Orbitals that are on that atom and that atom and that atom and that atom. Right? So we're advancing the discussion up to this point. We're not there at all, but we'll read about that. Right? All right, resonance structures. Second thing is doing it on the paper, drawing resonance structures. And this is where we get into pink, and pink is really red and white. Okay. Whenever we have resonance, we often draw red and white, and then say, hey guys, the true structure is a blend, it's really pink. That discussion. This is actually a tough molecule to do resonance with because there's no polarity. When we have polarity, that'll sort of give us a guide of how we need to move electrons based on that polarity. But I'll do it anyway because it's sort of what we've been talking about here. When you do resonance structures, all you do is move pi electrons. For example, I could move these and just put them there. What does that arrow mean to you? That arrow should mean that I have just moved pi electrons onto this atom and it becomes what? Instead of it being a bonding pair, I'm moving the two back to the atom to become what? A lone pair, yes. That's what that arrow should mean to you. And now I have that structure. Do I have any charge now?
Minus.
Yes, that's now minus. And this is what? Positive. Okay, how many H's on this carbon? One. There's still one, 3 bonds positive. Okay? That's a different structure over there. What is it? It's a resonance structure. Why is it a resonance structure? Because all I moved was what? I only moved pi electrons. Did I move any atoms? No. One of the golden rules was all resonance structures have same net charge. What's the net charge of this? It's a neutral molecule. What's the net charge here? Neutral. See? If all of a sudden it becomes just minus, then something's wrong. All right? We can draw other resonance structures here. This is good. Positive. How do you stabilize a positive? Move electrons towards it. We can move these, but that'll just give us this back. What if instead I do this? That's the old windshield wiper. It's not moving over here to become a lone pair, it's just doing this. Like a windshield wiper. What does that electron movement give? Double-headed resonance arrow. It gives boom, boom, boom. Double bond now here. Yeah? Nothing changed here. And what's now here?
Plus.
Now the positive is there. And we'll finish up here if we can. It's another resonance structure. And we can keep going. And we'll have to redraw these when we pick this discussion up, because we'll add more here. One thing we'll say is, which is the best structure of these three? And here the obvious answer is what? This is the best structure. Okay? Drawing resonance structures, we need to learn common arrow movement. And I'll call it the windshield wiper, or we'll do the old in and out. That's the windshield wiper. Okay. Please be doing some reading about resonance. Okay. Next Friday, we'll pick it up and we'll get it into gear and we'll be moving ahead. Okay. So no class on Monday. Test on Wednesday. Thank you. See some of you this afternoon in lab.